Okay, Assalamualaikum warahmatullahi wabarakatuh. The last video is actually on the we are moving into the closed loop control of DC drive, right? We have to think, we have to understand that the purpose of doing this is we want to operate the motor at certain speed, and when there is a disturbance in terms of the load or anything to the system, you can still maintain the speed at a certain speed requirement. Is that it? So there must be a control, a closed loop control, so that it can automatically adjust the speed of the motor regardless of the whatever disturbance or whatever load that you put into the motor. So it can sustain, or it can sustain the speed, or if you want to move to another speed, then you can adjust and tell the motor to drive at particular speed. And also we have to think about the quadrant operation, so you can instruct the motor, you can tell the motor to work into in quadrant 1, quadrant 2, quadrant 3, quadrant 4, right? So just to give you some refreshment, I always upgrade, by the way, I will always upgrade the notes. So I'm going to tell you wherever we have a new version of the notes of the slides. Okay, right. So come back to the last slide. So last presentation, and we have this feedback system. Okay, so the one that we discussed last week is on only for that particular transfer function of the motor, DC motor, and we just only look into the separately excited DC motor, right? And you can apply the same understanding, the same theory for the series converter, series motor, but now for the purpose of explaining the whole system, how it works, we only touch on the separately excited DC motor. Okay, so last week we talked about this, and this video will discuss on how we're going to do the complete system of the closed loop, right? So you start with the modeling the motor, and we start with the come back there. Okay, so this is the complete system. We start with the steady state equation, steady state equation to discuss to model the motor operation, right? And we have this equation. This is the steady state equation, you call it, right? The back EMF, the KVL across your armature winding, right? And this is the Torx equation. Okay, and then from that steady state equation, we develop the model, so we can look at the behavior of the motor itself in terms of voltage, speed, and current as well, right? And finally we found out that this is the okay, only for the model of the motor, okay? So we need the equation for speed, and then we give a feedback, right? And then this is actually to present the steady state equation in terms of Laplace transform. Okay, and then from that, the whole system here, we can see that how the load and how this reference voltage, okay? This is not the input voltage, this is a reference voltage. Reference and input is a bit different there. Okay, and so what happens to the motor here if you subject to the load, torque, and reference signals change? Okay, and we finally found out that this is to represent the speed and the reference voltage. So this is transfer function to represent that, and that actually come from this when you set the TL equals to 0. So the complete system, we have this complete system, open loop, call it open loop system, and to get the response of the speed in terms of the change in the VR, we're going to set this equals to 0. We're going to set this TL equals to 0. Okay, we're going to set that equals to 0. So therefore, we have this block diagram here, whereby you set the load equals to 0. So you have this transfer function to represent the speed against VR. Okay, and we call it as a G omega V. Okay, next is we look into the load change. What happens to the model, the behavior of the motor subject to the change in the load top? So when you do that and you rearrange the model here, okay, so you're going to set the VR equals to 0. This is 0, so therefore you don't have that. Okay, and you arrange, remember this is negative feedback, and therefore if you look at the block diagram here, then we have this negative there. Okay, and we rearrange, there is no VR, so here VR equals to 0. So by doing that, we have the transfer function of omega s against DL, the load top, in terms of Laplace transform, and we define what is a torque. Is that mentioned here? What is TA? I did not put that. So mostly all the notes here is actually come from the Rashid's book. Okay, Rashid's book. So I think I missed this. This is the armature time constant, right? The motor time. This is the mechanical time constant. I need to put that. Or you can refer to Rashid's book. What is a torque A? What is a torque M there? Tau. It's not torque. Tau. Tau A. Tau M. And the rest of the equations. And finally, then when you can use the final value theorem, where you set S equal to 0. From there you can find the step change. This is a step change of delta omega with respect to the step change of delta VR. And then there's change in VR and what is resulted into the speed change. Okay, so you have this equation, and then for the load change, we set this, and we can look at the step change in the delta omega. And therefore, if you want to, this is a superposition, right? Superposition. But if you want to consider both responses, which is both are done simultaneously, for example, then you just add both of these equations here to get the final omega m, like, oh sorry, if you want to get the final delta omega total subject to the change in the voltage as well as the load torque. Right, so now we're going to move into modeling the converter itself. Remember, we have the DCDC converter, we have a single phase converter, we have the three-phase converter. So that actually we have to look at, we already looked into the models of the motor. Now we're going to look into the model of the converter, and we combine all together and to make it as a closed loop equation. So now we focus on modeling this converter. Okay, so the first type is the DC-DC converter. So now you have to think of what is the control parameter of the converter. If you talk about DC converter, DC-DC converter, so what is the control parameter here, control variable for DC-DC? It's a duty ratio, isn't it? Not the input voltage, but the duty ratio. Input, we're going to consider, of course, the input will always, nominal, it has a constant value, isn't it? We have constant input voltage. What we can do into this to the converter is we just change the duty ratio. So by changing the duty ratio, your output voltage will vary. Okay, so for in doing that, we need uh, a transfer function as well. And for the DC-DC converter, we have this KR. Okay, and that KR equals to the duty ratio. K is the duty ratio. Sometimes you put as a D, sometimes it's a delta, eh, whatever it is. But this is the duty ratio of the DC-DC converter. So that will relate between the, you have to look at VC is the control signal voltage, and normally in the circuit, in the control circuits, we have 0 to 10 volt or 0 to 15 volt. It limited to a very low voltage in terms of control signals. It doesn't mean this is the duty ratio here actually does not look into the whole converter. Yeah, I mean, because normally we have a converter that the input voltage is 200 volt, for example. Then we have duty ratio. That so now K is actually the ratio between the control signals VC and VCM, which is the maximum value of control signal voltage. So here we have 10 volt or 50 volt. So let's say that we have 10 volt. So VCM is 10 volt, and therefore you need to have a K so that VC will be changed, isn't it? So the value of VC will change, and that will control the whole input voltage to your motor, right? So you just take that KR is equals to K duty ratio, which is equal to VC over VCM. And next, for single phase converter, remember we have this equation, isn't it? That will actually give the output voltage of a single phase converter 2V peak divided by pi cos alpha, which is the firing angle. Right. So you change, if you change the alpha here, the firing angle, then the voltage also change. So the control parameter here is the alpha. So once you have that, then that actually represented in terms of VC over VCM. So that gives the ratio of this VCN is the nominal, we call it normalized, normalized VC, which equals to VC over VCM. So once you change a VC and VC here, alpha also change, right? When alpha is changed, then output voltage of the single phase also change. That will actually affect the motor, because you change the armature voltage. Remember, we have the armature voltage before. Okay, so from that equation, just follow this, and finally you find out that KR equals to 0.9 multiplied by Vs, which is the supply RMS voltage, okay, divided by VCM, which is the maximum control signal. Here we have 15 volt, 10 volt, 15 volt, right? So that define KR for single phase converter. And next, this is the same equation here, same equation there. For the average, I should have removed this. Actually, I should have removed this because we have that in the previous slide. Okay, so here, let's look again. So I'm going to remove that. Okay, all right. For the average output voltage, so we have this equation, VA equals to 3 multiplied by root 3 V peak over pi cos alpha. So again, when if we change alpha, then we have the different value of for that. So for here, we normalize VCN, and if you get into that, you have the KR. Okay, So your KR here is the gain of the three-phase converter, and now it is defined by 3 multiplied by root 3 Vm over pi VCM. And if you convert that, substitute that in terms of single phase supply phase voltage, then you have where Vs is the per phase voltage. Okay, this is a phase voltage RMS divided by VCM 2.339. And so that defines KR. Right. So next, therefore, a converter can be modeled with a transfer function GCS of a certain gain and phase delay as described by this equation. Right. So you have KR and you have three different converter, DC-DC converter. You have single phase converter and three-phase converter, and that represents the transfer function of the converter itself, which can be explained. You can also represent this in terms of 1 plus S tau R, and tau R is known as a delay time. It is a delay time, and you can calculate actually what is the delay time based on this equation here. Okay, you can find, for example, you have Fs equals to 60 Hertz. Okay, 60 Hertz, 1.389 for a three-phase converter, TR 2.083, and for a DC-DC converter. So you can calculate that, and that will give you the value of tau R, okay, tau R, which is we call it as a delay time constant. Right? Okay, so that's for the converter models. Now we're going to look at the closed loop transfer function once the models for motor are known. We have known that the motor feedback path can be added to obtain the desired output response. To change the open loop arrangement in the figure below into the closed, the speed sensor is connected to the output shaft. So we need to have, there you are. Okay, so just now it's only for that output voltage equation, the steady state equation of the motor, isn't it? And this is required omega that. But now in terms of the automatic closed loop control, so the speed here need to get back to the system, and that speed now actually become the control to the converter. Okay, so that's why we have this statement here just now. The output sensor, which is proportional to the speed, is amplified by a factor of K1 and is compared with the reference voltage VR to form the error voltage VE. So you convert that omega S, okay, by means of K1 here, the factor K1 here, and that changed to VB. So therefore you have this reference voltage here plus minus, so the the error result from this comparison will drive the converter in terms of alpha, in terms of duty ratio, isn't it? So convert to duty ratio here, or alpha here. It can be alpha, it can be duty ratio, right? And therefore we change the whole motor, and then we can change the speed of the motor here. Okay, so when you do that, when you add another, it become cascaded, isn't it? Cascaded block diagram. So you have add another loop, outer loop there, and that actually so now again, just what we did in the modeling the motor, we also need to consider the change in the load, change in the reference signals. Okay, so now we look again. So we start with the closed loop step response due to a change in reference voltage can be found from figure above. The transfer function becomes, okay, so you want to see the change in what happens to the system when you change the reference voltage, and now you set TL equals to 0. So here there's no TL, is it? So previously we have the summation and we have the dot L here. So just now we have this summation here. then you have torque here, isn't it? Negative. So now we remove that, we set that into the 0, and we look into the response, and we have this equation: omega s over VR equals to K2 KVIF. So again and again, please refer to Rashid's book. Rashid's book, page, you can look at page, did I start from Rashid, page 174, isn't it? 734. So you can look into starting from 734. You can refer to that and look into the derivation, everything, the derivation, and everything's actually taken from the Rashid's book. Okay, that's that. Keep that. Okay, and next, so we're going to look at the reference. What happens with the speed as you set omega as a reference voltage and TL equals to 0. So solve that, and we have this transfer function, omega s to VRS. Next is to consider the load, the torque. We want to consider the torque and let VR equals to 0. Okay, so next slide. Okay, the response due to a change in the load torque can also be obtained from figure below by setting VR equals to 0. Therefore, if you look at here, there is no VR, is it? VR equals to 0, and that should, the negative feedback there should be represented by -1 input. This is not in the book. I redraw that. Okay, I redraw this, and you have that just to show you how we get the transfer function omega s divided by load torque here. So that represents everything, and you can refer to the book again, or I need to improve the slide. What is TA, right? What is TM, tau M, tau A, tau M, and what else? That's all you have. Okay, so next, the steady state in change, just what we did before. The steady state in change in speed delta omega due to the step change in control voltage VR and a step change in load torque can be found from equation 15 and 16 by substituting s equals to 0. So you now have a change. What happened? The change in the speed in regard to the speed change, the change of the reference voltage delta VR. Sometimes it's written as delta VR, delta here. Sorry, theta. It is not theta. Delta, isn't it? Delta omega, delta. We have that triangle symbol here, and this is to represent the speed in respect to change in reference voltage. This is the speed in terms of load change. Okay, so this two equation there. Now we look into the converter drive. Now we look into the equation, the questions. So we have a 50 kilowatt power, 240 volt. This is RMS voltage, VS. 1700 RPM separately excited DC motor is controlled by a converter as shown in the block diagram below. So it just represents in terms of block diagram. The field current is maintained at constant IF equals to 1.4 amp, and the machine back EMF constant is 0.91 volt V divided by A rho. So this is actually, if you refer to the previous note, kV here actually represent, so kV actually represent KIF, if you just remember, KIF there. And that's why you have we start with E equals to K flux omega Z, and then if you have a constant flux constant field winding, constant flux. So we have K, then that represent K, another new K, K I F I A. Okay, therefore you have K, new K, which is KV here, equals IF IA. Okay, and therefore omega K plus there's mistake here. This is not IA. This is omega Z. KV. So KV equals to IF omega. Therefore, KV equals to E divided by KV equals to IF omega, and that's why the unit is voltage divided by A radian per second. So that is 0.91. That is KV. The armature resistor RM 0.1, the viscous friction B 0.3, the amplification of the speed sensor is K1, and the gain of the power controller is K2 equals to 100. So you just plug it into that equation. Determine the rated torque of the motor. Determine the reference voltage VR to drive the motor at the rated speed. If the reference voltage is kept unchanged, determine the speed at which the motor develops the rated torque. And the load torque is increased by 10% of the rated value, determine the motor speed. If the reference voltage is reduced by 10%, determine the motor speed. If the load torque is increased by 10% of the rated value, the reference voltage is reduced by 10%, determine the motor speed. If there was no feedback in an open loop control, determine the speed regulation for the reference voltage VR equals 2.31, determine the speed regulation. It's very long equation here. So the book, this again taken from the Rashid's book. Right. So now all informations are given here. So this is solution. Okay. So you start with the rated torque. TL equals to 50K divided by 17. So we know that power or torque equals to omega T. Power equals to omega torque. Therefore, torque equals to power divided by omega. Okay. So that gives you 280.87 Newton meter. So because VA equals to K2 VR, VA for open loop control. Does it given? Is there anything whether it shows whether it follows DC motor? Nothing mentioned, but here it follows that we have VA equals to K2 VR for open loop control. We have that. Okay, at rated speed. Oh, sorry, not that. And then feedback voltage VB equals to K1 omega 95 times 10 to the power minus 3 plus times, so that gives you 16.1. So with closed loop control, so now we have VR minus VB multiplied by K2. So you are given the reference voltage minus the the feedback voltage from the speed, and that gives you 230.98. The reference voltage 90.22, and from there now you have the delta omega. So we have delta omega equals to minus 2.04. So it is a reduction in the speed. So you have the speed at rated torque now becomes lower, which is 1680.5 RPM, or you can convert that into radian per second. It's the 175.98 compared to 17.02 speed. Next, we have this load torque change. You follow that, and you have this torque, the motor speed, and come back to delta VR. I hope you go through the solution. It's very straightforward. Okay, you just need to apply the equation and understand whatever information is given to you, which is which, and finally you have that here. Okay, so that only actually for the we're not actually doing a closed loop. So this is the converter control models. Okay, so you have omega, okay, one. So that only up to the converter models. When we talk about controlling the whole system, you have to think on the what we call it, the compensator. There is another circuit which is known as a compensator circuit that will complete the whole closed loop operation of the motor. Okay, so up to this point, we actually, yes, we have a closed loop, but it's only up to the change in the reference voltage as well as the load torques. Okay, that's only in terms of closed loop, in terms of motor and the converter. The final stage is actually to put in the compensator circuit as well into the circuit to make it stable. So with this compensator circuit, right, now we can actually stabilize the output voltage to stabilize the speed of the motor. If you don't include this compensator circuit, for example PI controller, okay, PID controller, if you don't do that, you will not have the final, I mean the speed cannot be stabilized. It will fluctuate. So you have to consider that to have the complete control circuit. So up to this point, we actually, yes, we do the closed loop model, but only up to the converter. Okay, so next video will be on how we're going to complete the whole system there. Okay, all right. So again and again, you have the, now you have this book, isn't it? The copy. Okay, so everything's in there actually. I try to be consistent, but I found out some of the symbol here is not consistent, right? It's not, for example, KC, KR. In that case, I will highlight in my slide. So you need also to compare between the slide and the PDF file from the Rashid's book here. Okay, so thank you, and we're going to have another video on the closed loop operation. Thank you. Assalamualaikum warahmatullahi wabarakatuh.